Okay, so let's look at blockchain and cryptocurrencies. So in this presentation we'll look at some typical cryptocurrencies such as Bitcoin. Then we'll look at some Bitcoin addresses to see the actual format, how we can create the public and the private key. And from there we'll look at some blockchain methods, and especially looking at how we can mine for a consensus. After that we'll look at Ethereum, and then also onto smart contracts. So the diagram at the top is our existing financial infrastructure. So with this, if Bob wants to pay Alice some money, then Bob contacts his bank and then says he wants to pay Alice a certain amount of money and gives her account ID and her sort code. That's then used to be able to transfer money from Bob's account into Alice's account. So Bob has what you could define as a ledger within inside Bank A, and all the transactions that relate to Bob will be listed in a ledger, so the bank at any time knows how much Bob actually has in his bank account. In a cryptocurrency world, there is possibly no need for the bank in between, where it is possible for Bob and Alice to transfer a payment between themselves without actually involving the banks as trusted entities in between. And with this we use cryptography to be able to create the trust within the connection and the transaction. So rather than Bob sending the transaction to Alice, what happens is that he will get Alice's ID, and then he will say on a blockchain that he now transacts a certain amount of payment towards Alice, and that should come out of his account. So the blockchain itself just acts as a ledger that actually defines at any given time how much Bob has in his account, so that we don't end up double accounting. So double accounting means that he would pay the same transaction twice, or he might use the same money twice. And also we know in the blockchain if Bob has enough money to carry out the transaction. For this we bring in the concept of miners who must agree a consensus as to whether the transaction between Bob and Alice is a valid one. So this is the model that we have for blockchain and for cryptocurrencies. So Bitcoin started somewhere around 2009 by this individual here. We don't know if he is the person who's been identified, but he is Satoshi Nakamoto, and it is thought that he created the first Bitcoin transaction, and he also drafted a paper which outlined the methods that we're going to look at. With this, there's no need for a central government to control the currency, or no organisation, no banks, and there is no need for a broker to actually manage the payments. Inside a Bitcoin network, what we do is we mine for the currency, and we'll see how that is affected later on in the lecture. Bitcoin itself is split right down into the 8th decimal place, where we have a Satoshi, which is worth 0.0000001 bitcoins, or it's 100 million of bitcoins equals to one of these. Okay, so that's our Bitcoin infrastructure, and what it is it's designed to reach a limit of bitcoins inside the infrastructure, and then there will be no more created. What happens is that there is a reduction in the amount of bitcoins which are released into the market, and that should continue to reduce. To make sure that this supply of bitcoins reduces, then the reward that is given to miners reduces over time, and every so often we see a halving of the reward. So it started off at 50 Bitcoin rewards, and it was cut to 25, and in 2016 it was cut to 12.5. Along with Bitcoin, there are many other cryptocurrency methods. There's Ethereum, which is Ether, Ripple, Litecoin, Monero, Ethereum Classic, Dash, Steem, Kilocoin, and Augur. So the Genesis record was created in 2009, as we can see here. The reward for this was 50 Bitcoins. And what basically happens is that we take the transactions over a certain amount of time, typically 10 minutes, and then we bring them together, and then the miners will race to find a hash for the newly created block. So in this case they find a nonce value, which will allow the hash to be created with a certain number of preceding zeros. And the difficulty is defined here. So in this case the difficulty wasn't that difficult, but it's increased over the years. Okay, the size of the first block wasn't actually that big because it didn't really have many transactions. In fact, it only had one transaction in it. And this is the transaction here. So this was the transaction that was made by the creator of Bitcoin, and you can see it was for the mining process, and this transaction has never actually been cashed out. So if we look at our blockchain information, so all the information on the blockchain is openly available on the internet. The IDs are pseudo-anonymized. So if we go back to block 0, so these are the most recent blocks that have been mined. We can see who they've been mined by, what the size is, and the total amount of Bitcoins, and the number of transactions. And we'll go to the first block, which is this one here. So you can see the previous block isn't there, so there's no link to the previous block because there was no block, and then there is the link to the next one, and there is the preceding zeros to make sure that the miner will mine with those numbers of zeros. So if we look at the transaction here, this was the payment for the very first Genesis record, and we can see here that lots of transactions have went into this account, but there's been no export, so money hasn't been taken out. So the total received is 66.7 Bitcoins, and it's still sitting there. So the creator and whoever has this account hasn't actually taken the money out, and it's just sitting there. It's reckoned that there's billions of dollars sitting in related accounts to the person who created this this record, or the first miner. And there's a few other ones that are interesting. So this account here has 1,210,000 Bitcoins been received, and there's still a fair amount of Bitcoins actually in there. When you think that Bitcoin values could be between 6,000 and 7,000, then this is a considerable amount of money. So the actual value can be extremely large, as we can see here. So there's been quite a bit of movement on this account, and it's not the largest Bitcoin wallet on the internet. This one here shows a single transaction of 2,034 Bitcoins. If we have a look at it here, you can see there's quite a considerable amount in there. And when we look through it, let's look at the next one, this one here. This, I think, is one of the largest transactions. It's 13,000 Bitcoins, which equates to $85,942,000 at the current time. So there's 85 million being transacted here on this date. So let's trace where that money goes. So that was at 8:04. So now let's look at this account here, which got most of the Bitcoins. We can see that the final balance is 0, so the money has went in and it's went out again. So we can see here that there was another transaction here. The money came in and the money went out to here. So we'll follow this one again. This is the money in and we end up with 0. So again we see that the money is now flowing here just a little bit later on. So this is at 1817. So we're now tracing through onto the next block, and we can see at the 1826 that money came in and then it went out again and it went here. So we're watching a lot of money flowing through different accounts. So we can see here again there's 84 million onto this account, and again and again. So Bitcoin, there's a worry about Bitcoin that it is used in money laundering purposes. Again, we see this money going through another account and on again and so on. So often you see this basic trail of money moving through different accounts, which makes it very difficult for law enforcement to be able to track the accounts and find out where the money is actually going. So you can see here again it's still flowing. We're up to 11 o'clock nearly now, and we see another transaction and the money is on again, 5 to 11, and so on. So eventually it'll come to a stop. The money will stop in a certain account from there, but we're seeing masses of money flowing through different accounts here. It still hasn't stopped, and so on. Okay, so you can continue on from there, but there is a worry that Bitcoin is used in crime related activities. Okay, so that sort of outlined some of the transactions there. So with every transaction we can actually see the flow of information from and then to, and then the amount of money. So the very large amount of money that, as we've seen here, was transferred. And it took a while for Bitcoin to take off, but basically it really started between 2011 and 2012, where it started to increase the number of transactions. But after that, really it's shown an almost exponential rise in transactions. There's obviously peaks and troughs as the market is starting to settle, but we're seeing a general increase in the amount of transactions. In fact, the amount of transactions started to fill up the blocks, so we had what was called a soft fork, with a soft fork, the miners agree to be able to change or update their parameters. So we've now looked to increase the block size to make sure that the transactions can fit into each block. The trading volume is really up and down again, but generally going up with some spikes, obviously, as the value goes up or down, then we'll obviously see spikes. So this might be someone bailing out of, or a lot of people bailing out of Bitcoins, or it could be a run on them too. Bitcoin value is really accelerated over the last year, from under 1,000 to now nearly 7,000. That's a times 7. But obviously it could go the other way after this, or it could continue on like that. So we've not really seen a stability yet in Bitcoin value. So let's look at Bitcoin addresses and how the addresses work, and how we actually create a transaction. The crypto is based on elliptic curve, where we can create a private key. So it's quite a large private key, 256 bits. What we then do is that we then generate the public key associated with that private key, and we use elliptic curve DSA for that one. It creates a 512-bit associated public key that goes along with the private key. So initially we create a random seed, a random number, and then we use what's called base 58. So you probably came across base 64. Base 58 basically takes out the characters which, and the base 64 characters which can be confused, such as an O and a 0. So you see here that we only see an O and we don't see a 0. So 6 of the characters get dropped out, and we end up with what's called the WIF private key. So that is then stored in Bob's wallet. If Bob loses that key, then he's probably lost his Bitcoins. So all transactions are signed for Bob with his private key, and then checked with his public key. So we generate this 512-bit public key. We then take a hash of it with SHA-256. We then do a RIP AMD 160 hash on it, and then eventually we do our base 58 again, and we end up, as we've seen, with this public ID. So if someone wants to send Bob some Bitcoins, they will use the public ID. That transaction goes on the blockchain and will be associated with Bob. Whoever is sending the transaction will sign that with their private key. So the private key must be protected and stored. So this is obviously a focus of attack, especially if it's on a website or hosted somewhere. No electronic coins get transmitted, so the coins aren't on Bob's computer. The only thing that Bob has is his private key, or his key pair, which should be protected. Okay, so there is Bob's address there. Okay, and then there's the hash of the transaction too. Okay, so there's the basic operation. There's the private key. We create the WIF private key from that with base 58. We generate the public key, and then we create the hash of it that we will use to verify Bob's identity. Okay, so here's an example: private key, public key, the WIF, the address, and then this is what a signed transaction might look like. Okay, so here's a transaction. It may have changed a little bit, but this is the kind of core of it. So there is an output. So Alice gets Bob's ID. She says the amount to send it with. She will then sign with her public key and find Bob's ID. She then adds the previous hash of the record and then adds her own public key she adds her signature of the public key and then adds the public key onto the blockchain. That's then passed to the miner, and the miner will then gather all of the transactions that have happened in the last 10 minutes or so and then bring them all together and try to compute the hash of all the valid records. If Alice tries to overspend, then the miner will be able to pick that up and know that it's not a valid transaction. Okay, so now let's look at some blockchains. So what happens is that the miners will fill up each block with transactions and then will race to find the hash of that block. Okay, so each miner goes ahead and then tries a nonce value with the transactions and tries to find a hash value which has a certain number of preceding zeros. The one that wins will create a consensus with the other ones, and they'll all agree on as a consensus on what the current block looks like. So in this way we will replicate the blockchain over many systems. So as long as one of the blockchains exists, we can replicate the whole infrastructure again. So it's a good thing for resilience. So this is an example of the miners who have successfully generated the hash. So we can see that a large percentage is run by very big mining companies here, but there's still quite a few smaller ones who manage to successfully mine from them. So a worry is that one company becomes dominant over the other ones and then could actually take over control of the Bitcoin network. So hopefully it will still always look a bit like this, and there are still opportunities for other companies to be able to win in the mining race. So we can look at that in terms of the stats that it shows in terms of the charts. We'll just have a look in real time. Okay, so we can see the time between blocks is about 10 minutes or so from there, and just have a look at some of the charts. This is the amount of Bitcoins in circulation. I think we're up to about 16.6 million here. Okay, so there we are there. So there's the winners, the companies who win most often. But we should be able to see for our current blocks. You can see Via BC won this one here, and they also won that one there. And that's the ones that they were successful in. Okay, so they will be paid 12.5 Bitcoins at this current time for that mining process. Along with this, the hashing rate that's required to be able to successfully calculate the hash increases over time. So we can see here, this is the current hashing rate that's required to be able to successfully crack the massive hashing rates, and probably only big companies with large banks of GPUs can be able to support this type of throughput for hashes. And then the mining process itself is looking for a hash. So we take all our records and then we add a nonce to it, random nonce, and then recompute the hash. And what we want to find is the nonce value, which will allow us to create that number of zeros. And you can see it in each of each of the blocks. We'll see these zeros at the start of it. So computationally, we make it more and more difficult over time to be able to compute this hash. That's to reduce the amount of currency and also to overcome the advancements in technology. Okay, so here we are here. So we can see there is the hash that's been computed with the zeros, and there is the previous hash. And then there is the next block. So we can see our hashes are all zeros in there. There's the winner there of it. The size is typically about 1 megabyte. That was the original size of the block. But recently we've had a soft fork which has increased that size, because really the transactions were filling up the block, and a transaction would have to wait to the next block, which obviously delayed the blockchain infrastructure. Okay, so let's look at a practical example of a blockchain, and that's with Ethereum. And Ethereum is one of the most popular blockchain methods, and it brings in the concept of smart contracts, which really starts to ramp up the applications of Ethereum, of blockchain. So blockchain was just created in 2015, and it built on the concept of the blockchain, the Bitcoin using blockchain, but it brought in the concept of having a smart contract, a trusted contract that could be run in code and could be run off the blockchain. Unfortunately, it was hacked in 2016, and they had two options. One was to roll back the clock to 1 day before, so that the hack didn't exist. But the other one they took was to actually fork the code with a hard fork. So that created two cryptocurrencies, Ethereum Classic and normal Ethereum. So both exist now and can be traded, but they split their blockchains. That was a hard fork. The reason they didn't go for the rollback is that it could have compromised the whole of the blockchain methodology, because one person or one group could actually say that they didn't like the blockchain and could roll back to a time maybe when they had more money. So the split in the currency was probably a good way forward for that one. So this is what happens. Our transactions come in, and our miners will mine and find the new hash. So we use the KitKat 256, or which is also called SHA-3. So SHA-3 is a completely new hashing method that's not derived from SHA-1 or SHA-256, but it's completely new, and it's much more optimized for IoT and for this type of application. The reward for in Ethereum is gas. So to create a gas takes 30, the miners are rewarded with 30 gas elements, and then if we have 256 bits of data, we add 6 gas units onto that. So for every transaction that we do, the miners are rewarded with a certain amount of gas. So they are obviously keen to perform the mining and incentivize them. Okay, so it's really a unit of work that we have. 30 gas for creating a hash, 6 gas for 256 bits of data. And in this way we keep our contracts small and they will be less costly. So that's basically a fee that the miners will receive, and the miners will obviously charge for the work that they are given. If the gas value is high, then the miners are often quite keen to do the work because they will be well rewarded. If we put the gas value too low, then the miners might not want to do the actual work. But they will only take the payment for the work that they actually create. Okay, too low, and the miners probably won't want to do the transaction. And if it's high, then the miners will be keen to do it. Once you pay to the miner, then you can't get the money back again. Too high, and there'll be lots of eager miners, and it's likely that your transaction will be prioritized. But they will return back excess gas that they've not actually used. Okay, so there's also a block size, and if your contract is too big, the data is too big, then it will overspill into another block, and again that will be charged from them. So really the focus is on not wasting bandwidth and also optimizing the CPU utilization. So the final concept that we have in Ethereum is smart contracts. So with smart contracts, what we have is that we have a contract between Bob and Alice in this case, and we can enact a contract which they both know about, such as Bob might want to buy a concert ticket, and the smart contract will say that he'll get 10% discount if he buys it within a certain amount of time, and then if he cancels within 1 week, he gets 80% of his money back. If he cancels within 1 day, he doesn't get any money back. The smart contract might enact so that people are paid at certain times and so on. So this really changes the way that contracts can actually be defined, and we can actually codify things much clearer. So what we do is we compile into Solidity, and Solidity will allow us to take our JavaScript program and then compile it into some sort of bytecode that we can actually run. So this is the compilation here. So we're taking this program here, and then we compile it, and we go for a Web3 deploy, which is a JavaScript deploy. We can run it as bytecode. It's a bit more difficult to deploy. So we take this code here, and you can see the bytecode is built in here. It actually defines the web account that we're going to run it from, and it's going to define the gas that we're going to use that hopefully will be mined. So what a future could look like is something like this. So we have smart contracts, which will define things like benefits and so on, and then we have attestations. So an attestation might be that we sign something. In this case, the GP has signed that Robert has diabetes and is also over 60 years old. We have those attestations, and we prove the identity, and they're signed. And then we provide these to smart contracts. In this case, Bob will get free bus travel if he's over 60. So if he has this claim here, automatically he will get free bus travel. And then in this case here, if he has diabetes, then automatically a smart contract will kick in, and then he'll get a discount from Boots. So in this way, we don't actually have to be continually filling in forms and so on. We can create a one-time claim, and then we can enact the smart contract. Okay, so that's been an introduction to blockchain and cryptocurrencies. I've got some demos and a lab that you can do to be able to build up your experience from that. So thank you.